before we jump in?
It's 11:30.
Okay, so
11:30.
the terrestrial planets, right? These are the closest planets to the sun, and they all share a compositional similarity. They're all smaller and denser, made of rocks and metals, have solid surfaces. And having solid surfaces, we can talk about, right, how much solid surfaces there are in the solar system. And I showed you this webcomic last time, or last time we talked about terrestrial planets. My excavating is this. I like this because it just gives you a sense for what the amount of solid surfaces in our solar system. And so kind of imagine stitching kind of a globe where you stitch together all the solid surfaces. Here's the Earth, right? All the solid surfaces of the Earth make up something close to half of all of the solid surfaces in the solar system. Then you have the large terrestrial planets, Venus, well, large in the sense that they make up a lot, right? So you have Venus, Mars, there's Mercury. Mercury's kind of small here, it's Mercury. But then you also have the Galilean moons. So now these aren't planets, but these are terrestrial materials. So we have the Galilean moons. That is the moons of Jupiter, Io, Callisto, Europa, Ganymede. You have a large moon of Saturn, Titan. You have our moon, the moon, right? You have smaller planetoids like, or dwarf planets like Pluto. And then you have asteroids here. You have various other small moons and comets here. Anyways, this gives you a nice overview of all of the solid terrestrial material in the solar system. Now, how do we know, besides just seeing that these objects have solid surfaces, how do we know what they're made of? How do we know that these things are dense? How do we know what's inside these terrestrial planets? So one of the things is we can just look at their average density. Density is total mass divided by volume, right? So we see how large an object is, and we can see its mass through its orbit, its orbital characteristics. So we get its average density. Now, it doesn't tell us, it might be that its core is denser than its surface, for example, but that overall, what we find is that the terrestrial planets are about 5 times as dense as water. Whereas the outer Jovian planets are about the same density as well. Okay, we can learn through earthquakes. We can learn about through the magnetic field of planets, and I'll talk about this. We can learn about what's inside based on the fact that the only way a planet can create volcanoes with lava and so on is if it's hot in the inside. And we can also look at little variations in the gravity on the surface of the planet, telling us what's below the surface. So here's just a joke comic by The Onion. NASA frantically announces mission to Earth's core after accidentally launching a rocket upside down. The point is right, we don't have a way of directly accessing what's inside the planet. We can drill down. We've drilled down many miles, but we've only really scratched the surface. We can't drill to the center of the Earth, and no one's come remotely close. So we have to use indirect means of trying to figure out what the Earth is made of. So first of all, right, the average density I talked about, right, if you just take the size of something and divide it by its mass, find its average density.
Don't do that.
If it's more dense than water, it must be heavier stuff, rocks and metals. So the terrestrial planets, Mercury, Venus, Earth, and Mars, are all much denser than water. Water has a density of 1 on this planet.
No, it's not.
Okay, the asteroids are also denser. And then you have the outer Jovian planets, Jupiter, Saturn, Uranus, are less dense. And then the trans-Neptunian objects, which are comets, are also less dense. Okay, so this is that pattern of composition I talked about before that shows the difference between planets and then Jovian planets. And another way, besides the average density of God's planets, is through earthquakes. Now, earthquakes have, if you've ever learned any geology or learned about earthquakes, you've probably learned that there's 2 types of waves that come from earthquakes. That's actually how we can figure out and pinpoint where an earthquake came from. It's because whenever there's an earthquake, you first get hit by one kind of jolt, and then a few seconds later, or even a minute later, you get hit by another jolt. One of them is called a P wave. Okay, you can think of it, the P is standing for pressure, meaning the wave is due to, so if the earthquake starts here and it ends up, you feel it over here, what's transmitting that wave is pressure. It's called a longitudinal wave. It's like a sound wave, that kind of wave. So it's illustrated here. It's like if you have a slinky, you plug on the slinky, you see there's a dense region that kind of travels along. That's called the P wave. But there's another way that the Earth can shape. It can slither sideways. Okay, that's called an S wave. You can think of the S as like being like a snake, slithering sideways. So that's illustrated here. It's like waving back and forth. And that has a different speed. Okay, so you can tell P waves from S waves, and you can use that to figure out where an earthquake came from. But also they have different characteristics. So S waves, for example, can't travel through liquids, okay? Whereas P waves can. And so this is really useful. So if like you have an earthquake on one side of the Earth and you don't detect it on the other side of the Earth, or you don't detect the S wave on the other side of the Earth, you detect the P waves on the inside of the Earth. That's because there's liquid on the inside of the Earth. That's one of the ways we know that part of the structure of the Earth's interior is you get down towards the center and it becomes liquid, it becomes molten. And more generally, you can use this technique. It's sort of like ultrasound. It's like X-raying the interior of the Earth using the sound waves from earthquakes. So we have the Earth is covered in stations that can detect vibrations of the Earth, and you can use the different speeds and different characteristics of S and P waves to learn kind of what's in the inside of the Earth. And so what we learned is kind of what we would expect. And this is called differentiation. When the Earth formed, when all the planets formed, everything was hot. Why? It's because it started out as this cloud of gas and dust attracted, and gravitational energy has to go somewhere. It goes to the east. So everything was hot. And when things were hot, they were molten. And when everything's molten in a liquid, light things rise to the top and heavy things sink. So early on in the history of the terrestrial planets, they became differentiated, meaning lower density and stuff floated to the surface, and really dense stuff like iron and nickel sank to the bottom. Okay, and so the planets have this sort of structure. They have dense stuff, they have a core of dense stuff, and they have less dense stuff near the surface. So here are the interiors of the terrestrial planets. Earth has a core that looks about roughly the size, and that's a region that's the highest density. Okay? So there's a lot of metal. Less dense stuff shown in kind of an orange color. It's called the mantle. And then the very surface, you can imagine the lightest, even on the surface. Venus looks very similar. Earth looks very similar. Mercury, as we'll talk about, has a very strangely large core. The moon has kind of a small core. Remember that? Resulted from a collision that the moon is mostly Earth mantle material.
I know, man.
And so one thing I want you to know is, right, why doesn't differentiation happen? Well, differentiation happens because you start out with
I don't know how to spell ice cream.
some stuff is heavy. And it has to be liquid, right? It has to be able to flow. That allows the light stuff to rise and the heavy stuff to sink. So in this example, it would be both B and C that I'd be looking for. And related to this, I want you to answer questions like, why does the core of a planet contain a lot of metal? right? Why is it mostly metal for the terrestrial planets? Well, it's because during differentiation, the densest stuff, metals, sank to the bottom. And it did this at a time when the planet was hot, so that everything was liquid. So if we look a little bit more closely at the interior of the Earth, it has an average density a little bit more than 5 times the density of water. And that's because a large part of it is a core of iron and nickel, which are more than 10 times the density of water. So really heavy metals make up a huge amount of the Earth. Next, you have the mantle, which is not quite as heavy. It's not all just iron and nickel. It's stuff like oxygen, silicon, magnesium, stuff that's not quite as heavy. And then finally, there's this thin crust that's made of oxygen, silicon, aluminum, and is the lightest region. Okay. Now, this oxygen, by the way, you might think of oxygen as a gas, but in terms of the solid Earth, right? Oxygen can oxidize metals. So you have oxygen, like oxidizing iron. You get iron oxide, for example. Oxides combine with all kinds of minerals, including silicon. Silicon dioxide is sand, for example. Magnesium dioxide is a type of mineral. Okay. All right. So why were the planets hot, and why are they still hot if they are? So we're going to talk about that. You may or may not know, if you go dig deep into the Earth's, go down into a deep cave, it gets hot. So actually the Earth still is hot. And in fact, it's molten on the inside. Now, one of the reasons why the Earth and other terrestrial planets may be hot on the inside is called primordial. They're still hot. They're still cooling down from when everything was hot in the early solar system. So to some degree, all planets are still warm from the early solar system. Another related reason is accretion, meaning especially early in the solar system, there was lots of impactors, right? All the planets were bombarded, right? Remember, by meteors. Okay, that heated up the planets. Okay. Further, just differentiation itself, that process whereby light stuff rises and heavy stuff sinks. That's a process by which gravitational potential energy, right? When heavy things sink, you're using up gravitational potential energy, and so that has to go somewhere. It goes into heat. So all these 3 reasons are reasons that originate from the formation of the solar system and are still causing heat today in the planets. But on Earth, actually, the prominent reason the Earth is still warm is what's called radiogenic. Okay, heavy stuff sink to the center of the Earth, right? And some of that heavy stuff is radioactive, like uranium, potassium. The kinetic energy of this stuff, I mean, you've probably heard of like the core of a nuclear reactor is hot. So that's like the core of the Earth includes heavy stuff that's radioactive, heating up the interior of Earth. And in fact, that's why, without that, Earth would have cooled off most of the time. Okay? But the Earth, it would still have a substantial amount of heat that was primordial, but Earth is as hot as it is today because of continued radiogenic heating. And then the last type of heating isn't important to the terrestrial planets, but we will see that they are very important for the moons of Jupiter, which are terrestrial. Okay, so the terrestrial moons of the Jovian planets do in fact get heat from somewhere, and the main place they get heat is called tidal heat, due to the fact that the Jovian planets are so large, they kind of pull on their moons and cause them to kind of get squashed and squeezed and heated up through friction. So here on Earth, though, right, I mentioned radiogenic heating. Here's just showing, how Earth has cooled off over time as the sources of radioactive decay have slowly decayed away. Remember, we talked about how potassium, for example, has a radioactive half-life of about 1 billion years. Uranium has a half-life of a few billion years. So overall, these sources of internal heat have been decaying away. So the Earth has been cooling off over time. And when we talk about heat, it's important to remember the ways that heat can be transferred, right? There's convection, so imagine a pot of boiling water. The bottom gets warm. That warm water on the bottom of the pot starts to expand and rise, okay? And you get illustrated by these black arrows here. You get convection. The pot begins to, the water begins to move and allow fresh cold water to come in and get heated. So that's one very important way that heat can be moved around by the water or any liquid physically moving the warm stuff around. Okay. Next, an example is conduction. Now that would be an example like the handle of your pot would get hot, like the metal, for example, just gets physically hot, and that heat transmits through conduction. For example, into your hands. Right? That's why you need like gloves or oven mitts or plastic over your handles so you don't get burned.
Where did it even go?
Well, conduction requires some solid for the heat to be transferred through, but it's not getting through. But it's not moving. It's not molten. Right? The way the water is when it's moved by convection. Okay, and then finally, the third is called radiation. Radiation is heat transferred by light. So, if you're sitting by a fire, you feel the heat. Not because wind is blowing to you, not by convection. Not by conduction because you're not touching it with a stick. You just feel the heat. That's the light, radiant heat coming to you through the vacuum of space. Right? That's how the heat gets to us from the sun. And one question then, right, thinking of all these three ways that heat can transfer from one object to another, how does a planet cool down? Okay, and to answer that question, let's first just think about a cup of coffee. Right? How does a cup of coffee cool down? Well, to some degree, it's heating up the air around it. That air brings cold air toward the coffee, and then that cold air gets warm, and you see that steam rise and it comes up.
Oh yeah, this is looking great.
But a lot of it is radiation. Okay? That is, even if that cup was in outer space, it would still be cooling down. And if there wasn't air cooling down, it would still be cooling down because it's radiating, right? Remember we talked about black bodies? If you took a thermal camera, you would see it's hot because it's radiating infrared radiation. And the larger it is, the larger the surface area is to radiate away. But the surface area goes as the square of the size of something. The mass goes as the cube, because the volume goes as the cube. So you probably have an intuition about this. A small cup of coffee cools off faster than a large cup of coffee. That's because of the volume to surface area ratio. That is, for a small cup of coffee, the ratio of its surface area, the way it's losing heat through its surface out into its surroundings, the ratio of that to its mass, the stuff that can hold on to heat, is smaller for a small cup of coffee. For a large cup of coffee, it has lots of mass. So here's just that general concept I described for if you model something by a sphere, its surface area goes as 4 pi r squared, its radius squared, but its volume goes as 4/3 pi r cubed, the radius cubed. So if you take the ratio of the area to the volume, it depends on the radius. That is, the larger the radius, in other words, the larger the size something is, the larger its volume to surface area ratio. In other words, the time it takes something to cool is proportional to its size. Okay? If you have a cup of coffee that's twice the size, it takes twice as long to cool. Similarly, the same is true for a planet.
Okay. The best part.
Exact same thing is true,
You really
especially because a planet is spherical.
invested.
So for a planet
Oh,
that's twice as large, it's twice as large and cool. And this is relevant to how hot the inside of a planet is. And we can tell based on its size.
what do you think the next one's gonna be? Look up here.
You see a small planet like Mercury, a small, not a planet, but moon, like our moon compared to a planet.
Wait,
That is expected to have cooled off faster from the beginning of the solar system compared to, say, a large terrestrial planet like the Earth and Venus. Okay. And as a result, the moon, for example, and Mercury are what we would call geologically dead. That is, they have cooled off enough that we don't see volcanoes on Mercury. We don't see volcanoes on Mercury. We don't see rivers of lava or a churning of the surface back down into the center like we have on Earth, plate tectonics. Right? And this has important consequences. And there's other characteristics about the moon and Mercury, as we'll see, that make this obvious too.
Madison, try on the glasses.
So
I guess
before we get to that, to these characteristics that have to do with whether a planet is geologically active or dead,
but they won't come off.
how do we know based on what we talked about whether something should be hot in its interior and therefore geologically active? How big it is. So first, I want you to be able to rank the 5 terrestrial worlds, including the moon in this, because it's large.
Time to draw a
Compared to
star.
all other moons in the
First,
terrestrial planet.
intersecting lines. And then I'll start connecting them.
Rank them by
All the way
size.
around
Well,
like this. Now for the remaining
remaining
lines.
for you. So the moon is the smallest. So we expect that to have cooled off a lot, geologically dead. Mercury is the next largest,
Something I can see in the line.
also geologically dead. The biggest is Earth and then Venus. So those you might expect to be pretty hot on the inside still, and therefore have volcanism and all these, we'll talk about all the other interesting things that come with that. Okay? Mars is an interesting case, it's kind of in between. That's another thing we're going to talk about what that means, okay? So that's something to remember. Moon is smallest than Mercury, Venus is the largest, Mars is in between.
Unfair.
And
Time for your final.
there's kind of interesting consequences, by the way, of this general rule that don't even just apply to planets. So Bergman's rule is an example of the same thing, the same concept of the fact that a smaller cup of coffee cools off faster than a big cup of coffee. It's the same concept as a smaller planet cools off faster than a big planet. You see this in
Not yet.
animals that are colder planets tend to be larger because they can stay warm. And so here's an example of Sweden, for example, where if you look at the species of moose in Sweden going north direction where it's colder and then south where it's warmer, and you plot them, you see that the average size of the moose is larger in the north and smaller in the south. So you see this all over the place, not just for planets and cups of coffee, because it's easier to stay warmer if you're on a larger volume to surface area.
Calm down, Annie. Just use the big pencil.
Any questions so far?
No way this pencil lead will break. Time to draw the best bunny.
So
I knew
one of the most important consequences of whether a planet is geologically active and therefore warm in the center is whether the planet or whether the terrestrial world has a magnetic field.
Madison, excellent
So
bunny.
let's talk about the Earth's magnetic field. So the Earth has a magnetic field. It's strong enough that right, you can use a compass. It's kind of cool. Anywhere on Earth you see compass will point towards the Earth's north pole. That's because the Earth's north pole is actually where there's the south pole of the Earth's magnetic field. Right? So if you imagine the Earth is like a giant bar magnet, near the Earth's north pole is the south pole of the magnet, and near the Earth's south pole is the north pole. And what does the needle of a magnet point towards? Well, the north pole likes to point towards the south pole of another magnet. That's why with the Earth's magnetic field having the south pole near our north pole, the north pole of a magnet points towards our North Pole. In general, we can think of these lines representing magnetic field lines. And one way of thinking about magnetic fields is that near the North Pole of the Earth, the field lines are coming in towards the center of the Earth. Near the South Pole of the Earth, the lines are coming out. And a compass needle will want to align with those magnetic field lines. This has consequences on the Earth that you can even see with your eyes. So near the North or South Pole, you'll see auroras. So aurora borealis in the northern hemisphere. Here's a picture from a space station, an international space station there. Or wait, maybe this was a space shuttle. So they're orbiting the surface of the Earth. They just point their cameras out. We see these beautiful patterns. Let's see. Click on this. Yeah, so here you see a movie from, okay, it looks like the International Space Station. So as they're orbiting the surface of the Earth, they see beautiful auroras, which you can also see if you're near the North Pole. I'm sure you've seen plenty of pictures of it, but this is a really beautiful illustration here.
What's up with him? Oh, look, that guy needs help. Hey, what are you doing in my room?
And where did they come from? They come from the fact that the Earth's magnetic field interacts with the solar wind from the sun. So the sun is producing lots of charged particles that are constantly flying through the space from the sun to the Earth. Okay, and these include the sort of charged particles that can produce light, that can produce electromagnetic waves, and they do so when they spiral towards the north and south pole of Earth's magnetic field. So a charged particle, if you put it in a, it's like an electron, if you put it in a magnetic field, it's going to spiral and release light. So these are actually charged particles from basically the radiation coming at us from the sun, getting kind of trapped by Earth's magnetic fields and generating light. So they're kind of like storms of solar radiation interacting with our Earth's magnetic field. And those storms of solar radiation that come towards the Earth produce belts of radiation that are trapped by Earth's magnetic field. Now, Earth's magnetic field is actually useful for life on Earth. It helps protect the Earth. It gives us kind of a cocoon that protects us from a lot of the radiation that comes from the sun. Like charged particle solar wind radiation that comes from the sun gets kind of trapped by these magnetic fields. So it's an illustration where here's the solar wind coming towards the Earth, and you see these patterns of magnetic field lines from Earth's magnetic fields, kind of create a shield around the Earth. Now, some of those charged particles get kind of wound near the north and south poles, where they generate those auroras, and then lots of them don't never actually hit the Earth because Earth's magnetic field is protecting us. And you see, because the wind is blowing here from left to right, it kind of shifts that envelope, kind of like if you're blowing on a candle flame. You see, it's kind of pushed to the right. And by the way, if you are an astronaut, you have to be careful not to go through these radiation belts because they can give you a pretty high dose of radiation. These are called the Van Allen belts. And something I haven't said yet, but this helps remind me, is that of the terrestrial planets, the one with the strongest magnetic field is the Earth. Okay? This is related to the fact that the Earth is largest. Okay? Earth is largest, geologically active. There's something going on near the center of the Earth that's causing this magnetic field. Okay? It turns out, so I'm going to say some more about this in a bit, but it turns out this is due to what we call a dynamo. The interior of the Earth, because it's molten, it's hot, it's rotating. Okay? And it's spinning like the same thing you might use to create a magnetic field. You might spin electricity in a circle that generates a magnetic field. That's how you produce a magnetic field in an electrode. The same thing is happening in the Earth's interior. You have this conductive stuff, this metal, iron, and nickel, spinning around very quickly, producing a magnetic field. Okay, and in order to do that, you have to have a molten interior. So you have to be a big planet that stayed warm and has a magnetic field. Now, Venus doesn't have a very strong magnetic field, even though it's kind of large. Okay, why might that be? Well, it doesn't rotate. Remember, this was one of these 3 exceptions in our solar system, where Venus doesn't rotate in the normal direction. Well, it barely rotates at all. And that means that its interior probably isn't rotating. And it doesn't produce a dynamo that creates that could create a magnetic field. So in our interterrestrial planets, Mercury and the Moon don't have much of a magnetic field because they're geologically dead. Mars, remember, this is an in-between case. We're going to talk about Mars. Venus and Earth both have what it takes to kind of create a magnetic field. Earth does because it's spinning. Venus doesn't because it's not spinning. Okay, now what other things go on when a planet is geologically active? Well, let's look at the Earth. So Earth, if you look at its interior, a large part of it is molten, okay? And the very surface of it is the coldest, right? It's this crust, which is rigid, it's not too hot. But just below that, we have a large region called the mantle that we say is plastic. Now that means deformable. It's molten enough that it can move maybe just a few centimeters per year near the surface, but it's like a sludge that's moving. Okay. And it can form convection patterns. We'll talk about. That is, the hotter stuff down in the center wants to float and rise. So hot stuff rises just like in a pot of boiling water, and then cold stuff is denser, so it sinks. So you have these convection patterns. Where you have rising stuff, you get things like volcanoes. Okay? You go deeper, you get to the core. The core has 2 sections. And the core is, first of all, very dense metal, iron and nickel. It has 2 sections. It has a liquid metal. And this is part of what's we also have a rotating solid core, the inner core, where the pressure is high enough to take that liquid and force it to be a solid. It's very hot. Now, you can imagine that if this planet is mostly liquid, it's going to be resurfacing the surface all the time, right? I mean, it has a solid crust, but everything else below it is constantly stretching around. You can imagine that over millions of years, the crust will keep being renewed. And this is what we see in these geologically active planets like Earth, Venus. And what's something really obvious that you can tell that's true? You don't see craters on the surface of the Earth or on Venus. Okay? Now that's not because you don't get meteor impacts. It's because whenever we do, we erase them by having geologically active planets that repave the surface. So if you look at the planet, that's one of the things we look for. We look for impact craters. Okay? Most of the craters came from early on in the solar system's history, when there's lots of impacts going on. Generally, impact craters, as a general rule of thumb, miles across. That means something, many dozens or hundreds of meters across is what impact craters. So look for impact cratering. Things like the Moon and Mercury are just covered in impact craters. We don't see too many on Earth. Volcanism. Okay, volcanism can reshape the surface and fill in molten rocks used out of volcanoes, right? Can cover in craters. So that's what happens when you have a geologically active. Another thing that happens is what's called tectonics. Right? The atmosphere. The crust moves because it's kind of floating on liquid that's underneath. And as we discussed about erosion. That happens a lot on a planet like Earth because Earth has rain, it has wind, it has storms, it has snow, it has rivers. that cause erosion. There's a thick atmosphere. You don't see that on a lot of them. So one of these things that's kind of unique to Earth is called plate tectonics, but it's a result of the fact that Earth is geological. And we talk about the convection in the mantle. So just below the Earth's crust, you have this hot stuff rising, cold stuff falling down, stuff moving like a sludge. And because you have stuff following these kind of dotted arrows, that means you have regions where stuff is being renewed on the surface, and you have regions where the surface here is moving to the right, regions where the surface is moving to the left, and then regions where the surface is going crumpling back down here. In other words, the surface is being repaid. And the main source of heat for this on Earth, to keep it warm enough to continue doing this, is radioactive. Also a large source of heat because Earth is just water, so it's taking a long time. Okay, and on Earth it's a few centimeters per year. So that means it's over every year, for example, the coast of the United States, further from Europe. If you fly to Europe, it's going to take you another second to get there after a few hundred years. Getting further apart. The Earth's surface is totally repaid. Primarily on the continents, I found a little islands that are floating on top of this region. And you see this illustrated in this cartoon here, showing what we have are what are called mid-ocean ridges, where that hot stuff coming up from the mantle, from that ridge. So, and then moving a few centimeters per year to the right from this ridge, and a few centimeters per year to the left from this ridge. So you're expanding that ocean floor. And it has to fall down beneath somewhere. So maybe you reach the coast, you get a trench, and you go down underneath the continent. And where that happens, you tend to get a crumpling up of mountains and volcanoes along that coast, right? So you see this all across the place, where you have mid-ocean ridge, and then plates all underneath the continent, producing mountains and volcanoes along that region. Overall, here's just an illustration of main plates on Earth. Here on the North American plate, that intersects, for example, the Pacific plate on the west coast, where you have plates kind of moving up on the west coast. Actually, so there's a famous fault line, the San Andreas fault, at this plate, where actually moving a few centimeters. Like LA is moving north, and, you know, a few million years or okay. Yeah, spreading mid-ocean ridge in the Atlantic. So, like I said, the east coast of the United States is getting further from Europe every year, and so on. You see these plates all around the surface of the Earth, and you see places where, yeah, there's lots of food here, for example, there, because in this case, we have the Nazca plate going underneath. Famously, Mount Everest here, we have the Indian plate actually bumping up against the Eurasian plate. Here's an illustration of if we map the ocean floors, you can see very clearly kind of the outlines of the plates. These are mid-ocean ridges here. This is one of these things you can kind of see right away from the rest of the world. It's not heavily cratered. What does that tell us? It tells us that
5 minutes,
is young. Right?
Math class. Hey, don't break the plastic, you. You go to the room, Mahaya. You're not done.
When did she?
If those were gone, you have new surface. Okay, we talked about tectonic activities. Here's my first poll question. What is something that makes it more likely for a planet to have?
Are you done?
Take 1 second. Okay, good. Most people got this right. So you're more likely to have tectonic activity if you have a high internal temperature, right? It has to be molten. And that's usually more likely if you have a big planet. It takes longer to cool.
Remember this point? Hey!
Any questions?
3 minutes. 3 minutes. What the heck? When did you get that file?
And a few years. Give up easy.
Okay, so let's go through in a little bit more detail. The terrestrial world specific. So we talked about the moon. Here's a nice picture of the moon showing. Well, first of all, that it's heavily cratered. Okay, right? You see craters and black marks pretty much everywhere.
Stop!
You also see some interesting regions.
Stop it! I'm gonna break the glass.
Fewer craters. That tells you what? That tells you that these regions are newer. They must
Hey! Next is the glass. Stop it.
Giant impact hypothesis, right? We think the moon formed when the early version of the Earth collided with a large-sized planet Theia early on in the solar system's history, about 4 billion years ago. And not too long after that, all of the planets in the solar system were bombarded, including the moon, by what was called the late heavy bombardment. That is.
Stop it! Stop it! You're gonna break the glass!
Covered in craters.
You got 2 minutes and you go. Oh my God.
And most of the craters you see on the moon are from this time, because since then, the planets
What do you want?
stuff have continued to away a lot. There's not as many meteors. A lot of the craters are from that period, 4 billion years ago.
I'm terrified.
But there have been lunar Maria that filled in some of those craters. That was that are these
For what?
ancient
You
floods of
evil
lava
Moody?
back when the moon was still warm. It filled impact bases. So that is probably had impacts. That then, because the moon was still warm, caused lava to fill in these regions. So lunar Maria. The moon still has a small molten core. It is still warm in the center, but a lot of it is kind of frozen. In other words, it's really the core.
Stop it!
We would call it geologic.
1 minute. There you.
No dynamo.
Just
It
a math book.
doesn't have a magnetic field. Now, we know one of the reasons we know that they're bombarded is because of the moon rocks we broadcast the moon missions in the 60s. Also, a plot of this is there's an artist's illustration of what that time would have looked like. It would have been very, not a place that you could live, very hostile. But we see, so this is a plot showing, first of all, that this solid line shows the number of impacts we would expect
I know what
from
I'm
the
doing.
beginning of the solar system.
Wait, wait,
Basically,
wait.
you would expect from 4.5
Class,
first form.
class.
Getting older. You get fewer and fewer and fewer because all the things that cause meteors get cleaned away. Right? Planets, all that debris gets bubbled, right? And now we should get far fewer asteroid impacts.
It's swimming time.
When we've got
Class, go to class.
of rock,
Go to class. You math. Get your math book.
3.94 billion years ago, they indicate that there's some new surface for about 4 billion, 3.8. Indicates that there was an uptick of impacts. This is called the late heavy bombardment. Late heavy bombardment impact. All of the planets on the surface. You see the same thing in Mercury. Mercury is another small planet, a little bit larger than the moon, but still too small for geologically active. Like the moon, that's why there's no atmosphere. Weather. I promised to talk about. It's a really large iron. This is kind of surprising because it's different from all the other really large. There's a number of hypotheses for this. One that makes a lot of sense.
Where's your math book?
This is the sun. So when it was first forming, it may have been so hot that the only thing it could condense was iron and nickel. So just like how throughout the frost line, or you could finally have ice condensed before the frost line. You couldn't have ice condensed. It could have been before Mercury. You couldn't have rock condensed.
Where you from, man?
It has such a large iron and nickel core. It's so small, it's been geologically inactive for billions of years. So just like, it looks very much like the moon. The surface is just covered in craters that haven't been filled in. It does have things similar to the lunar Maria, as we'll see. These plains of magma from eruptions that happened billions of years ago. And now Mercury, it's kind of solid rock and metal, right? But it's changed temperature over the years, and things that get cooler shrink. So it has, when it shrinks, something has to give. It kind of causes these cliffs to form. So due to compression, it has these really, really tall, steep cliffs that haven't eroded because there's no water, or atmosphere, or rain, or rivers. It does have a very small number. So it's a little bit bigger than the moon. We think it has a tiny dynamo just in the center. It's mostly frozen and geologically dead. But in the very center, there's a bit of a dynamo sitting there. A small magnet.
Can you go in the
There's
room?
a radar map of the surface of Mercury, showing all these impact craters, but also these places that look like the Maria. Here's a nice, again, it's almost hard to tell, differentiate it from the moon. There's tons of impact craters. By the way, whenever you see these kind of star patterns, like here, kind of white, blue here, that's because you got an impact crater there. But whenever you get impact craters, you shoot lots of little rocks kind of flying out kind of a star pattern. Those rocks blow away. Those rocks are
Go in the room.
and as you see, you have tons of pock marks from meteor craters, but then you have these regions like this that are like the Luna Maria, where the craters were kind of filled in at some point 2 billion years ago. Here's a zoom in on one of these super tall cliffs on the scarp. They're like vertical cliffs, miles high. Next comes Venus. Okay, Venus is the first, going out from the sun. It's the first planet now that has, and also we talked about the moon. So neither moon nor Mercury have a atmosphere. Okay, Venus has the biggest atmosphere, the thickest atmosphere of all the terrestrial planets. Okay, very dense. Not so it's mostly CO2, but it's 90 times as dense as Earth's atmosphere. In other words, 90 times the pressure. It's crushing. The pressure is crushing.
Mama, don't laugh.
It has big clouds of sulfuric acid that make it.
Go in the big room.
And because of all
Go.
the, it has an extreme greenhouse effect. So it's hot. It's
Go to the
hotter
bedroom
to
now.
than it ever is.
Go.
Incredibly hot.
Dạ thôi có sĩ về bất cứ cái phố á.
You can image it, so even though you can't see through its clouds with visible light, you can use radar to map its surface. So I'll show those pictures. I'll also show pictures because there have been a few probes that landed on Venus. It happens to not have any tectonic plates, even though it is geologically active. It has the most volcanoes than any planet in our solar system. But like you would expect, it doesn't have very many impact craters. That's not because there weren't impacts. It's because, well, one, it has a really dense atmosphere, so it does burn up a lot of the impacts. But two, it's been resurfaced because it's geologically active. So here's a radar image from a probe that flew over Venus and probed the surface. So the orange regions are high, so mountainous, volcanic regions. Blue are deep, or valleys, basically, right? And you see that there aren't too many craters. Some of the things even that look kind of like craters are more volcanic in origin. Here's a large volcano on the surface of Venus mapped by radar. Here's another large volcano mapped by radar, and then use 3D software to kind of rotate it so you can kind of see what it would look like from the surface. Of course, the sky of Venus is not black. So this is just because this is an image straight from radar that's looking only straight down, and then it tries to show what the mountain features look like based on the radar data. And if you just look, if you try to look at the surface of Venus, you see clouds, sulfuric acid clouds. This is what it just looks like on the surface. But we have seen in visible light what the surface actually looks like. These are probes from Russia. They sent a series of probes called the Venera probes down to the surface. And so we've got quite a number of images that give us a pretty good idea of what the surface of Venus looks like. I mean, it has just normal rocky. Here's an image from Venera 9 probe, just kind of rocky surface, kind of similar to Mars or even Earth in a lot of ways. And here is a visible light image, so you actually see what the sulfuric acid clouds look like. So it's a kind of yellowish atmosphere and rocky surface. Next is Earth. Any questions so far before I move past Mercury, Venus, Moon to Earth?
Question about Venus's atmosphere. Is it sulfuric acid because of the heat, or what is it? What causes that?
I wouldn't say it's sulfuric acid because of the heat. It just happens to have sulfuric acid in its atmosphere. I don't know if I have a good answer for like why. I don't think I have like especially good answer for why it's sulfuric acid in particular, but that's just what it happens to be. Sulfuric acid, can form when you have some water available and some sulfur that can react. I don't know. Any other questions? Sulfuric acid, I think, is H2SO4, if I remember. It's made of hydrogen, oxygen, sulfur. Let's see, is that? So I mean, I think the main reason is that just there happens to be a lot of sulfur in its atmosphere. It might have something to do with the temperature. Maybe if it wasn't so hot, it wouldn't form sulfuric acid clouds. I'm not sure. So it's a good question. Maybe I'll look into that. Any other questions? Okay, so the Earth, just looking at it is kind of special, right? So it's, first of all, it's kind of blue, right? And that's because of liquid water, which you don't have any on any other planet, although we'll talk a little bit about Mars. Mars is kind of a special case that we'll talk about. But so Earth is very special, though. It's an oasis of life because it has a surface of liquid water. And also, this is kind of special because water can easily become a vapor like on Venus because it's too hot, right? If you make it just a little bit hotter, it'll vaporize and become hot. I mean, if you've even just been to like Florida, you know, the air is thick with water, right? You see how it just needs to be a little hotter for the air to start filling with water. And if it's a little colder, if you've been to, you know, up north or even just this last week in Chicago, right, it snows, water can turn to ice. So it's actually kind of special to have a surface with lots of liquid water. That's kind of hard to have. Earth, other just interesting things about the Earth, has a large moon that's relative to the Earth's size. This is, remember, we relate this to this giant impact hypothesis. Other special things is that we have an atmosphere, and it contains lots of oxygen. It contains ozone, which is also oxygen. It's O3, which helps protect us from ultraviolet rays. And we'll talk about why that is, and that's because the oxygen comes from life, actually. Life is what creates the oxygen on Earth, so that's why we're special in that regard. Why we can have liquid water is because we have a greenhouse effect, but one that's not so strong as Venus. Remember, Venus, its atmosphere is mostly CO2, right? Earth is special, it doesn't have that much CO2. It has some, but not too much. So we have a nice, just perfect balance of greenhouse effect. Okay, Earth is made out of mostly rocks and metals with a density that's about 5.5 grams per cubic centimeter. In other words, about 5.5 times the density of water on average. Here's a nice photo of the Earth rising from the Apollo 8 mission, where they didn't land on the moon. This is orbiting just over the surface of the moon and seeing the Earth rise. So let's talk a little bit about each of these. So liquid water, this is special. 71% of the Earth's surface is covered in liquid water. And that's what's so special. It's not just water. As we'll see, water is common in the solar system. That's not what's weird. What's weird is liquid water, because you have to, one, have about the right distance from the sun, right? So you're not too warm or too cold. But you also have to have about the right amount of CO2 in the atmosphere to have a greenhouse effect that's not like Venus. Now, Venus is way hotter than Earth. That's because of an atmosphere mostly carbon dioxide. So it's a really strong greenhouse effect. We have just the right amount of CO2 in our atmosphere. Oxygen. We have oxygen in our atmosphere, which is great for people like us that breathe oxygen. And actually, the only reason why our atmosphere, unlike other atmospheres, is filled with oxygen is because of smaller life. Okay. Early on in Earth's history, there was the development of photosynthesis, and small little organisms like algae photosynthesized and took carbon out of the atmosphere and locked it away in their bodies and kind of breathed out oxygen. Okay? And that filled the atmosphere with oxygen, whereas it didn't have oxygen at all before. Why? Because as we'll talk about in the case of Mars, oxygen tends to rust things. So a lot of the surface of a planet that had oxygen will end up, the oxygen will end up just in the form of minerals. Plate tectonics is special on Earth because of its role in stabilizing the amount of CO2 in Earth's atmosphere. The fact that the Earth's surface gets repaved every 100 million years or so means that over hundreds of millions of years, the CO2 in Earth's atmosphere, through what's called the geologic carbon cycle, gets kind of dissolved in the Earth's oceans and then kind of rain down as a precipitate on the Earth's the ocean floors, and then that gets brought down back into the interior of the Earth. Okay, so over long periods of time, Earth regulates its own amount of CO2, which is very special, giving us very long-term climate stability. Okay, meaning, luckily, the Earth doesn't turn into Venus. The Earth has plate tectonics that allow it to keep about the right amount of carbon in the atmosphere. Of course, this is now a big issue because when humans came along, we suddenly, over the course of 100 years, doubled the amount of CO2 in the atmosphere, which is way too fast for the hundreds of millions of years the Earth normally takes to bring the CO2 back out of the atmosphere. So this is now a problem, right, that we're dealing with in terms of climate change. And I'm going to have a whole lecture talking about that. So those are the unique features of Earth. Mars, okay, the last of our terrestrial planets, is really interesting and kind of special because it's on the border of a lot of these categories. Okay, so and there's a really interesting story about what happened to the water on Mars. Mars used to have liquid water. We're going to talk about. So, okay, let's go over some of the features of Mars before we get to that. One is when you look at Mars, it has kind of a very different looking north side compared to its southern side. Indicates there's probably a big impact at some point in Mars's past. And we also see evidence of past geologic activity. As some of the largest volcanoes in the solar system, they're not active anymore, but it shows that Mars did have geologic activity. I mean, and similar to that, when you look at Mars's surface, you don't see a lot of craters, right? So Mars, right, must have filled in those craters somehow. So it used to be geologically active. This makes sense because Mars is bigger than Mercury and the Moon, right? It's big enough maybe that it could still be pretty warm on the inside. But it's less big than Venus or Earth, so maybe it did cool off too much to be active anymore. And there's evidence that it used to have a magnetic field, not much anymore. So there's no current dynamo in the inside of Mars, but maybe it used to have it. Okay? So something happened in Mars past where it used to be like Earth and Venus, but it's just not big enough. So it kind of froze out at some point, got too cold, and its dynamo stopped and its magnetic field went away. And as we'll see, that will have a profound consequence for Mars's water. Let's see. It does have ice caps, but it's mostly CO2 ice. So carbon dioxide gets so cold it turns into dry ice. But there is evidence of past flowing water. It seems that Mars used to have not only rivers, but it used to have lakes. Okay, we can pretty clearly see that Mars used to have liquid water flowing on it, which is fascinating. Where did that water go? And is there life from that water? Could there still be life on Mars? We're still looking. In fact, there's a probe set to land in the next day, I think. So maybe I'll talk about that next time. Hopefully it's successful. It's very difficult to land on Mars because its atmosphere is a little thick, is thick enough that you'll burn up if you're not careful, but too thin that it's very hard to use the parachute. You just kind of fall. So it's very difficult.
You're not going to crack with me.
I've done it before. Okay, the other thing about Mars is it does have an atmosphere, but it's pretty thin. And it's mostly CO2. Just like, say, Venus's atmosphere, but Venus is really thick atmosphere. Mars is just a very, very thin atmosphere, so there's not much greenhouse effect. Let me just show, because we've taken some wonderful panoramic pictures. So here's a YouTube video of one.
When the Curiosity rover climbed a ridge and the skies.
Let's turn off the volume just so you can just look. So wonderful pictures. Right? Look at this. And I mean, it looks like, southwestern U.S. or something. Right? This is just a panoramic picture from Mars. Okay, and then we can see this because we sent rovers down that have explored. Anyways, Mars is wonderful. I have a couple other YouTube video links there that you should check out. So I'm going to close mine. Oh no, it's still here. Okay, so some other cool pictures. Here's someone with a ground-based like backyard telescope. Got this wonderful shot where they saw the International Space Station kind of crossing where Mars was in the sky. So here you get a cool picture of Mars and the International Space Station just from someone's little backyard telescope. Here's some pictures showing off the largest volcano. You know, here's a volcano 3 times larger than Mount Everest. Famous volcano called Olympus Mons. There's a zoom in. Here's from far away. You just see how big these volcanoes look even from outer space. So clearly Mars was geologically active.
You're not going to
Look at
class
the Mars,
women.
some crater impact pock marks, but nothing like this. So clearly it was geologically active in the past, smoothed over a lot of these craters. You also see an enormous canyon. It's the largest canyon in the solar system. We think partly what formed it was kind of, like a kind of a rift.
Take your iPad and
Geologic
go.
activity, not one big river. But you also see in some other photographs I'll show you, you do see that water did flow and produced erosion.
Take your iPad and go
Here's
to
from
class.
North and south polar ice caps. You also see kind of the difference in geology from the northern and southern
Take your
hemispheres.
iPad and go to class. Go.
Here's a much higher resolution photograph from orbiters that orbited and took really nice photographs of the surface of Mars. Here, yeah, so here you could see all these little kind of river erosion, signs that there was liquid water eroding, forming these kind of classic like riverbed patterns. Here's some tracks from one of our rovers that we've sent down. This is the Spirit rover, looking back at its own tracks over the surface of the kind of rocky, dusty Martian surface. Here's a Spirit and Opportunity rovers looking at minerals that formed from millions of years of water, just like on Earth, laying deposits, mineral deposits that form these layers, right? This is a classic sedimentary rock showing different layers forming in bodies of water. So there's very clear evidence that water previously flowed on Mars. And also, this is kind of detailed, so I won't go into the physics of it, but we can put satellites above Mars and measure how much water is hidden below the surface. And near the North and South poles, that's what this is showing, is that while we currently don't see big lakes of water on Mars, we do see bits of water hidden underneath the surface, kind of moist soil, frozen moist soil underneath the surface of Mars, indicating there still is some water, but there's still the question, where did most of it go? And we can still see when it's warm season on Mars, you get this. Here's a series of photographs showing you can actually see water coming unfrozen and seeping out down hillsides. Isn't that remarkable? So we can see evidence of water still being in liquid form on Mars, but there's just not much. So, and it's near about time to end soon. So maybe I'll leave you with this picture because we'll come back to this next time. Is that this is the history we think. Mars, about 4 billion years ago, was covered in water. And somehow that went away, okay? And that has to do with the fact that Mars is this intermediate sized planet that cooled off. And so its dynamo locked up. It lost its magnetic field. And its magnetic field was protecting it from the solar wind. And no longer protected by the solar wind started breaking apart the water into hydrogen and oxygen. The hydrogen floated away because hydrogen's too light. And the oxygen was just left over to rust the surface, which made Mars turn red. So that's where we think most of Mars's water went. But I'll talk more about that next time. Any questions before I let you go? All right, so we will pick this up next time. Have a good weekend.
Thank you, Professor.
Thank you. Thank you. Thank you. You have a good day.
Cool.
How's Nancy? Oh, Nancy. Why don't you go to class? What? Go to class! Oh my God! You're not talking no one at the other end. Shut up and go to class.